It is started. Yeah, the recording has started. So let me share my screen and then you can let me know. Only one or two students can let me know. Okay, can you see my screen?
Yes,
Yes,
sir.
sir.
Yes, sir.
Great.
Yes,
Okay,
sir.
fine, fine, fine. Thank you.
Yes, sir.
That's it. That's it. No need for everyone to say it. Okay, so let's start our serious discussion. Okay, so as I mentioned in the last class, so this is PH 1001 course. Okay, and this course is basically divided into two parts. One is the first part is special relativity, and the other part is quantum mechanics. Okay, these two parts, these two subjects, special relativity and quantum mechanics, are the pillars, modern pillars of modern science. Okay, these two are the pillars of modern mechanics, of modern science. Okay, so everything we see in the nature, almost everything, can be described from special relativity and quantum mechanics. Okay, and these two are also the subject which suggest that Newtonian mechanics is actually an approximation of these two theories. Okay, these two subjects. So Newtonian mechanics is an approximate mechanics of these two subject, these two theories, subject topics. Okay, so Newtonian mechanics, whatever you have learned in your kindergarten classes and your 11th 12th, is actually an approximation, in some way an approximation of special relativity and quantum mechanics. So Newtonian mechanics is not the true theory of our nature. Okay, so your course is to understand. So the idea of this course is to give you some flavor of special relativity and some flavor of quantum mechanics. Okay, so in the first part, that is from today, we'll discuss about special relativity. So let's discuss special relativity. Okay, so VT. So my handwriting is not good. Okay, so if it's not clear, then ask question. Okay, so if you have any confusion or anything, then you should ask a question. Okay, so what is special relativity? Okay, so special relativity is one of the most beautiful and elegant theory ever created by mankind. Okay, so this was developed by Albert Einstein in 1905. Okay, so 1905 by Einstein. Okay, and you will see it changed our description, our notion of time and space and all. Okay, so it just completely changed how we thought about daily the Newtonian physics. Okay, so there are two words, one is special and one is relativity. So what are they? Okay, so let us first understand relativity. What is relativity? Relativity means that all motions are relative. All motions are relative. Okay, that means the motions are defined with respect to an observer, or motions are defined with respect to an observer. Okay, so for example, a bus is going, so this is you. Okay, let's say this is you, and according to you, you are at rest. Okay, and then a car or bus is going in this direction. So let's say this is a car with velocity v. Now you cannot say that the velocity of the car is v. What you have to say is the velocity of the car is v with respect to you. Okay, similarly, for example, a person in the car, okay, let's say that is me. So I am sitting inside the car. I will say no. I am at rest, but you are moving in negative x with velocity minus v in the negative x-axis. Okay, so the motion are relative. You say I am moving, I am saying you are moving. So who is correct? Everyone is correct, but you have to define very carefully. The motions are defined relatively. Okay, so there is no absolute motion. So there is no concept of absolute motion. There is no absolute motion. Absolute motion. Okay. So if somebody say he is moving with velocity 100 kilometer per hour, that's a wrong statement. You have to specify that he is moving with 100 kilometer per second with respect to you, or with respect to me, or with respect to someone in uh, in Mumbai. Okay, so the motion is relative. Okay, so that's the first thing, that all motions are relative. In Newtonian physics, you can
Sir,
define, yeah,
sir, but speed of light is not defined with respect to anything, no, sir.
that we will see. That we will see. Just wait on. Right now, I haven't gone to speed of light and anything. Okay, just hang on, hang on. I'll define the speed of light as well. Okay, so yeah, so the motions are defined with respect to an observer. That is more important. Okay, motions are defined with respect to an observer. So that is relativity. The motion is a relative concept. Okay, now how do we define it? How do we measure the motion? Okay, in order to measure the motion, we have to define a frame. We have to define a frame. So this is called frame of reference. Frame of reference. Okay, so what is frame of reference? A frame of reference is a part of the of the description of the motion of the motion. It is a part of the description of the motion. A motion is defined with respect to some frame. U is one frame, me is another frame. Okay, or you can say a frame of reference, a frame of reference, a frame of reference is a coordinate system, okay, with respect to which, okay, which we, with respect to which we make measurements. Okay, by measurements you are calculating the motion, you are calculating the velocity, you are calculating the length, you are calculating the time. Okay, so measurement of any physical quantity.
So,
Just a minute, just a minute.
hello.
Yeah, just a minute. Of any physical quantity. Yeah, go ahead. Somebody had a question. Yes. What was the question?
It's clear, sir. It's clear, sir. It's clear.
Okay, okay, okay. So this measurement, okay, it's like a coordinate system. Okay, so this coordinate system can be anything. This coordinate system can be anything. For example, it can be x, y, and g coordinate. And at the same time, you have to define t as well. Okay, so suppose something is happening. So okay, how do we quantify that something? So for that we have to define what the position of that something. So how many position? X position, Y position, Z position, and we also have to define at what time that is happening. Okay, for example, a bomb blast happened. Okay, let's say a bomb blast happen. Suppose a lightning happen in Raulkela. Okay, so what we have to do? The lightning happen at Raulkela. So you can define the Raulkela coordinate x, y, and z, and we have to define at what time it happened. Okay, so you have to define x, y, and z as well as time. Okay, so this is called an event. Event. So event is something something that is happening that is happened at a particular place. Okay, that means you have defined x, y, and z at a particular time. At a particular time. Okay, so that means t. So here you have to define both x, y, and z as well as time. Okay, so this is the frame of reference with respect to which you measure it. You measure the motion. Okay, for example, let's say this is you. Okay, so you are at rest. Okay, and with respect to you, I am me is moving with velocity v. Okay, so this is your coordinate system. The motion is this. So your time is t comma x. Okay, I'll work only in x coordinate. Okay, y and z we don't worry about. We can insert it later on. Okay, you will say the according to you my motion is, so this is the vertical axis is t, the horizontal axis is x. Okay, so if you have to define my motion, according to you my motion is this, right? Because you will say x is vt, right? This line is x is equal to vt. Okay, so I am moving in this line. According to you I am moving in this line. Okay, now suppose what would be the motion of your line? What would be the line of your motion? Well, you are at rest. Okay, your x is not changing. Okay, your x is not changing, but your t is changing. So what would be your motion? The line of your motion? Your line of your motion would be this red line. So you are moving, your x is not changing, but your t is changing. So that is your line. Okay, so this is called yeah, so you are measuring your motion, and according to you my motion is this line, this tilted line. Okay, x is equal to vt. Any question? If you have a
No,
question, then ask.
No, sir.
no,
Sir,
sir.
you
No,
are
sir.
saying I am.
No, sir.
Yeah, somebody has a question. Yeah,
Sir, you are saying that we are rest with respect to us, sir, or
yeah,
with
you
respect to
obviously
you.
no, you are rest with respect. So yeah, please mute yourself. You are rest with respect to yourself, obviously, right? If imagine there is nothing in the universe, only you. Imagine there is nothing in the universe, only you. Okay, with respect to you, you will always be at rest because you cannot, unless there is an acceleration, you can feel a jerk. You cannot define whether you is moving or somebody else is moving. Okay, unless there is an acceleration. Okay, so that lead me to another point. Okay, so there are some special frame which is called an inertial frame. So inertial frame. Okay, so what are those inertial frame? Is a frame is a frame An inertial frame is a frame in which the laws of motion holds. The laws of motion, especially the first laws of motion hold. Okay, so it's a frame with which is either at rest. It is a frame which is at rest. Okay, or it's a frame It's a frame which moves with a constant velocity. Okay, so in all those frames, okay, which are either at rest or they are moving with constant velocity v, so that means the acceleration is zero, all those frames are inertial frame. Okay, so you sitting at your home is an inertial frame, me sitting at my home is an inertial frame. Okay, somebody in a bus moving with respect to us with a constant velocity is also an inertial frame. Okay, and the important point is physics says that the laws of motion holds in all inertial frame. Okay, the first law of motion holds in all inertial frame. Okay, so as you can see that that there can be infinite number of, there is no unique inertial frame. There can be, let me write it this way, there can be infinite numbers of inertial frame. Okay, there is no unique inertial frame. Okay, you at rest is an, let me write if for inertial frame, if me moving with respect to you at constant speed, constant velocity is an inertial frame. Okay, so there are no unique inertial frame. Okay, so what does it mean? It means that let's say something is happening at Raulkela. Let's say lightning happened at Raulkela. Okay, now you can measure that lightning. Okay, you can measure the coordinate of that lightning and time of that lightning. Of course, you can measure it in your frame. You will say it happened at this value of x, this value of y, this value of g, and this value of time. But at the same time, I can also measure that lightning from my frame of reference. Okay, I'll say no, it happens at this value of x, this value of y, this value of z, and this value of t. Similarly, one of your friend who is sitting at Mumbai, he can say no, it happened at this value of x, this value of y, this value of z, and this value of t. Okay, so we all are right in our own respective frame. Okay, so we can measure from our own respective frame. So there is no unique reference frame. Okay, there can be an infinite number of reference frame. So that's the uh, most important point. Okay. Okay, any question on this till now?
No, sir.
No, sir.
No, no,
Okay.
sir.
Okay. Wait. Okay. So
Hello,
if you
sir.
don't, okay, good.
Sir, how
No, sir.
frame of reference is unique, sir?
Just a minute. I'll make a comment. Okay. If you understand it, you don't have to say no, sir, no, sir, no, sir. Okay. Just stay quiet. Those who have a question, just let them ask question. Okay. So if you understand correctly, if I ask, okay, is this clear? You don't have to say anything unless if you have a question. Okay. Yeah. So somebody is, how unique is a reference frame? There is no unique reference frame.
Sir, every inertial frame contains reference frame,
Sorry.
sir.
Sorry. Can you repeat?
Every inertial frame contains a separate frame of reference.
Yes, it can be same or it can be different. Okay. So for example, you, yeah, it can be same, it can be different. Okay. So for example, suppose this is you. Okay. And this is your friend, but they are at rest with respect to each other. Okay. So this is your coordinate, tx and x, and this is your friends. Okay. Let me call it t tilde and x tilde. Okay, now you want to measure the point, this point, let's say P. Okay, so this point can be defined by T and X as well. So that means you are measuring it, and this P point can also be defined by T tilde by and X tilde. So your friend is measuring it. Okay, so yeah, there can be many references frame. In fact there can be infinite number of reference frame. Okay.
Sir,
Yeah.
sir, will it be possible to say that there can be an inertial frame in a non-inertial frame?
No. Non-inertial frame. Okay, all accelerating frames are non-inertial. All accelerating rating frames are non-inertial. Okay, non-inertial frame means accelerating frames. Inertial. Okay, non-inertial frame, and the laws of physics does not hold in non-inertial frame. Okay, so what does it mean? If the equation F is equal to ma is true in one inertial frame, it will be true in all inertial frame. Okay, but that doesn't mean that if the laws of physics hold in inertial frame, it will hold in non-inertial frame. Okay, so in that way, all accelerating frames are non-inertial, because then you can distinguish acceleration, you can distinguish motion. For example, just I mentioned, this is you, okay, and this is me. So according to you, I am moving with velocity v in this direction. This is according to you. I am moving with velocity v in this direction. Let's say constant velocity. But equally, I can say, no, I am at rest, but you are moving with velocity v in this direction. So this is you. This is from your point of view. Your point. But from my point, this is me. I am at rest, but you is moving in this direction with velocity v minus v. Okay, so the motion is relative. If the velocity, the relative velocity is constant, then if the laws of motion holds in your frame, then the laws of motion also holds in my frame. Okay, so that is what about inertial frame. But if our relative velocity is changing, that means acceleration. Okay, then we can distinguish which one is actually moving. Okay, so in this course we will not discuss anything about acceleration. Okay, these two descriptions are completely equal. Okay, I am moving with respect to you with velocity v in positive x-axis is same as you are moving with respect to me with velocity v in negative x-axis. So this is my point of view. My point of view. Yes. Yes. I could not hear you. It's yours. I could not hear correct completely. Yeah. Can you repeat it again?
Sir, anything in the universe can be initial and both.
Sorry, it's
Single
very
person.
difficult. Your sound is, yeah, it's not very clear actually. Okay. So maybe you can ask this
Sir,
question later on. Yeah,
Sir,
yeah, your sound.
anything.
I can't hear it clearly. I can't hear you clearly.
Sir,
Yeah.
Sir, you were saying that
for
acceleration should be 0 or net acceleration should be 0.
Sorry?
You are saying that the acceleration should be 0 or net acceleration should be 0.
The acceleration. Right now, so net acceleration here, I mean, there is only one x-axis. Okay, so I am dropping the y-axis and the z-axis. Okay, so net acceleration is just acceleration. Yeah, so there is another question.
Sir, for us to define a inertial frame, we need to be an inertial frame. So, are we in an inertial frame?
Well, exact inertial frame, there are no exact inertial frames. Okay, because with respect to, let's say, sun, we are in motion. And
Yes, sir.
okay, so suppose you are at sun and you see the motion of your friend on earth. So with respect to you, okay, so with respect to you, the motion of the frame of your friend is non-inertial, because we are constantly changing the position and the motion. Yeah, your friend is constantly changing the position and motion of her frame. Okay, so that is non-inertial frame.
Okay, sir.
Okay,
That's why we
so
take all as an initial frame.
sorry.
So that's why we take Earth as an inertial frame. For
No, it's a one frame. Okay, so actually, Earth is also a non-inertial frame. In a yeah, Earth is also a non-inertial frame because Earth,
our
for some
convenience,
different reason.
our convenience for solving question, we take Earth as inertial frame.
Yes, inertial frames. Yes, for simplicity, we are taking inertial frames. Yes, that's a good point. Yes, for simplicity, we are taking inertial frame because it's are easier to analyze. Okay.
Yes, sir. Thank you. Sir.
Okay, good. Now let's start. Let's say,
Right.
yeah, go ahead.
Sir, if we change the reference, it might be inertial and non-inertial, no?
No, no. If it's an inertial frame, if the velocity of your frame, the velocity of you is changing, then for me, you are a non-inertial frame. If your velocity is same throughout your motion, then you are an inertial frame for me. Okay? Okay, so let's start. Let's say V is equal to, V is my velocity relative to you. My velocity relative to you. To you. Okay? So your coordinate, so let me define first your coordinates. So your coordinates are t and x, and my coordinates are t prime and x prime. Okay, and I am moving with velocity v with respect to you in positive x axis. Okay, so this is the thing. So this is let's say t and x. So that means that's you. Okay, then this is me. So this is t prime and x prime, and I'm moving with velocity v with respect to u. Okay, so let's say this is the point, this. Okay, how the coordinates of t and v are related. So you can see very easily that x prime relation between your and my coordinates, relations between yours and my coordinates. Okay, and then you can clearly see that x prime would be what? X minus vt. Do you agree with this?
Yes,
Let's
sir.
say
Yes,
this is
sir.
the point. Okay, very
Yes,
good.
sir.
So you agree that x prime is x minus vt. So if I know your coordinate, if the information of your x and t are given, the information of x prime can be obtained. Right? Now what about time?
It will be same.
What about time? Okay, as somebody said, it would be same. Why it should be same? It is same because Newton told us. Galileo and Newton told us. What Newton told us? Newton's assumption. Newton told us that your time and my times are same. That all clocks or all time, all clocks are same. All clocks are same. So your clock and my clock are all same. Okay, so that means t prime is t. Okay, which is same thing. For example, you are at rest. Okay, and I am moving past you. I make a one circle and then I come back, and so I took a car and we come back to the same position, and then we match our clocks. There is no, there hardly you will notice any difference. Okay, we usually go out from home, come back, and then see the clock at your home and the clock at your watch, they always remain the same. Okay, so Newton told us t prime is t. Okay, so what are the transformation we found? We found that x prime is x minus vt and t prime is t. Okay, so this transformation is called Galilean transformation. This
Sir,
is
excuse
called,
me, sir.
yeah,
Excuse me, sir. Previous equation, can you make me understand once again, sir?
Galilean, just a minute, Galilean transformation. Transformation. Yeah, which equation you are talking about? This one?
Yes, sir. The first equation.
First, yes, second. Yeah, so what's the problem in first equation? So you just see, you are moving with velocity v, so you are approaching the point P, right? So for
Yes.
you, the distance from you to point P is actually, so this distance is what? This distance is x minus vt, because this distance is x.
Yes,
Am
sir.
I right? Because this
Yes.
distance is vt. Okay.
Oh, okay. Thank you, sir.
Okay. So this is called Galilean transformation. So it's a relation between two coordinate system. Relation between two coordinate systems. Okay. Now analyze the light ray. How the light moves. Okay. Let's analyze the light ray. Suppose in you are sitting at your home and then you switch on the light. You have one laser light and then you switch on that laser light. Okay. What is the velocity of the light? How light rays moves in your coordinate? Well, light moves with velocity c. Okay. So you would say x is equal to ct. Right? X is equal to ct. Very nice. But now analyze how light rays moves in my frame, in my coordinates, on my frame. My frame is good one. So let's write my frame. So in my frame, x prime is x minus ct. What is x? X you have given me, x is ct. Oh, sorry, x minus vt. I'm moving with velocity v. Okay, c is the velocity of light. Okay, and v is my velocity. Minus vt. This is what? C minus v by t. So there, that means this implies, according to me, light is moving with velocity c minus v. Okay, so what is happened? Yes, so what is happened? This is your coordinate. Okay, and you send a light. This is t, this is x. How this? My coordinate is t prime, x prime, and I'm moving with velocity v. So both light, okay, so both light, please mute yourself. Please mute yourself.
Very sir.
Please mute yourself. You have a
Atlee only, sir.
should I mute everyone or what? It's very disturbing actually.
Mute everyone, sir.
Just a minute.
Mute everyone, sir.
Sir, mute everyone.
Yeah, that would be.
Sir, please
Yeah,
mute everyone.
yeah, so that would be fine. Mute all. Okay. Yeah, so I have muted everyone. Okay. So yeah, so light is, suppose, so this is you and t and x is you and t prime and x prime is me. So you send a light. So I am moving with positive x-axis with respect to you, and you send a light in the positive x-axis. Okay. According to you, light moves with velocity c. Okay. But according to me, light moves with velocity c minus v. Okay. Similarly, you can say, okay, let me set light in the opposite direction. Similarly, for the opposite direction, direction. So you send the light in opposite direction. What did you do? So this is your axis t and x. Okay, you send the light in this direction. Okay, in negative x-axis. Okay, so this is light ray. I am moving with velocity v in the positive x-axis. This way with velocity v. So what is the velocity of this light with respect to me? Well, again, x
C
prime
plus
is
V.
x
C plus V.
minus, okay, x minus
C plus V.
vt. So that means ct minus vt is equal to, okay, so this is minus minus, so minus c plus v t. So that means light is traveling with velocity, light is traveling, according to me, traveling with velocity c plus v in negative x-axis. Okay, so in your frame light is traveling with velocity b, but in my frame light is traveling with different velocity depending on the velocity of me. Okay, so light,
Sir, I didn't get it.
which one you didn't get it?
The direction minus C plus V.
Yeah, so what you did is, so similarly in the opposite direction, that means x is equal to minus ct. Okay, so what is the graph of x is equal to minus ct in your plane? So this is your plane. This is t axis. This is x axis. Okay, so this line is x is equal to minus ct. Okay, I am not plotting x, y, and z. I am plotting t and x. Please see it. Okay, I am plotting t and x. I'm not plotting x as a function of, yeah, x, y, and z.
Sir,
Yeah.
sir, I'm not understanding x dash equal to x minus vt. How you are writing, sir?
Yeah, this is just I explained, right? Did you see it? The
Yes,
t
sir.
x. Yeah.
Before also I didn't understand, sir. How you are writing that?
Which part you didn't understand?
X dash equal to x minus vt. How you are
Yeah, that's I'm
writing that,
saying.
sir?
Yeah, again. So
Excuse me,
suppose,
sir.
just a minute. I'll take one question one by one.
Sir, I have doubt regarding this only. Sir, can you clear
Yeah.
the basic that we are at rest and the other person, our friend, is moving with velocity v, right?
Yes, fine, fine. It's okay. Fine. Yes. Yes, it's fine.
Sir, regarding to that, we are calculating all this, na?
Yes.
Okay, sir.
Okay. So yeah. So the question is, there is a point. Okay. Let's say there is a point. This point. Okay. This point exists. This event exists. Irrespective to what you are measuring, irrespective of you or irrespective of me. A lightning happened at Raulkela. It is independent how you are measuring or how I am measuring. It is happening. Now it's a stick or it's a coordinate system with respect to which you are measuring. So now this is you, t and x. You are at rest with respect to you. Okay. What are the coordinate of this point? The coordinate of this point is tx. Okay. Now I am moving with respect to you with velocity t prime and x prime. With respect to you with velocity v in positive x-axis. Okay. Now what are the coordinate of this point with respect to me? T prime and x prime, or t tilde or x tilde, or I'm using prime. So let's use t prime and x prime. What's the relation between these two? Well, at the same time, let's say time is time, t prime is t prime, which is what Newton told us. But what is the relation between x prime and t prime? By the time this t happen, this distance, okay, this point, okay, so this is where what I have shown here. According to me, this distance, if I know the your coordinate, this is just x minus vt, which is the x prime. Okay, if you are still confused about it, just think about it. Okay, just take 5 minutes and think about it. Okay, after the class you take 5 minutes and think about it, why x prime is x minus vt. Okay, if v is
Sir.
0, just a minute, if v is 0, that means there is no relative velocity between you and me, then x prime is same as x, no issue. Okay, but if go ahead.
So that lightning example, I can't get it.
So lightning example, you can't get it. Okay, a lightning happened at Raulkela. The important point is it happened. It is irrelevant who measure it. It is independent of who measure it. Okay, it happened. That is the fixed thing. Now it is independent of who measures it. I can use my meter stick. I can use my coordinate system to measure it. You can use your measure stick to measure it. But my coordinates and your coordinates are independent. Not independent, but the lightning does not depend on that. Okay, it happened. So that was the argument I gave. Is this clear now?
Okay, okay, sir.
Good. So yeah, so we see that the light is traveling with velocity c in your coordinate axis in your system. You are measuring it, but it seems to travel. So light seems to travel travel at different speeds on the reference frame, on my reference frame. So I'm moving with respect to you on my reference frame. Okay. Now that's a big problem. Why it's a big problem? It's a big problem because near the beginning of the last century, means 20th century, various experiments were done. Okay, in the beginning of the last century, various experiments were done. Okay, and all those experiments done, and in all those experiments people found that the velocity of light is same, and people found that the velocity of light is same in all coordinate system, in all reference frame. Okay, the velocity of light is same. That's an experimental fact. Okay, though Einstein claimed that he didn't knew about this experimental claim, he derived independently all the results of relativity. But it's an experimental fact that the velocity of light is same in all reference frame. Whether you measure it or I measure it, I'm moving with velocity v with respect to you, I measure it, we will all see that the velocity of light moves with, the light moves with velocity c. Now, that's problematic. If the velocity of light moves with same in all reference frame, that means this Galilean transformation is wrong. Okay. Newton would have agreed with this Galilean transformation. X is equal to x minus vt, t prime is t. Okay. In Newtonian mechanics, the laws of physics remains the same. Okay. So for example, suppose what is Newtonian physics? F is equal to ma, right? So what is a? A is the velocity of an object. Okay. So m is equal to du by dt. Okay. Now let's say this is u, this is u, okay, and with respect to you, a ball is moving. This is a ball. The ball can have any velocity, it can have an acceleration. Okay, the force on that velocity is, so ball is moving with velocity u. What is force? Force is m du by dt. Very nice. Now let's say I am moving with velocity v with respect to u. So this is t prime x prime, and I am moving with velocity v with respect to u. This is me. Okay, so I also see this ball is moving. What is the velocity of ball with respect to me? The velocity of the ball, let me put m here, that is with respect to me, would be what? Anyone? U minus v. U minus v. So now let us calculate the force. So force is in u, force is m du by dt, and the force with respect to me is also m d um by dt. So this is m d by dt. What is um? Um is u minus v, small u minus v. But this is m du by dt again. Why? Because dv by dt is 0. Because I am moving with constant velocity. So you see that the definition of force in your frame and in my frame remains the same if we use this transformation, this Galilean transformation. So Newton would have agreed. Newton would have happy. Okay, he said, okay, yeah, everything is fine. There is no issue. But because of this experiment, okay, that this experiment is called Michelson-Morley experiment that we will discuss later on. We found that people found that the velocity of light is same in all directions, in all reference frame. So that means something is wrong. What is wrong? So we have to find what is wrong. Okay. So we need to find out this relation between coordinate and my coordinate such that the velocity of light is same. So there is something wrong. There is something wrong in Galilean transformation. Please mute yourself. Galilean transformation or Newtonian mechanics? Mechanics. Okay. Okay. Then come Einstein. Okay. Einstein came and he suggested some radical changes. Okay. The first radical changes
वो म्यूट
was
नहीं किया सर वो नोट नहीं किया सर ऊपर वाला
mute हुआ नहीं. Okay, okay, it's fine. Let's we have 10 minutes. Let's discuss it. Do you have a class after this? Do you guys have class after this?
नो सर
No, sir.
Okay. Okay, good, good.
No,
So
sir.
you
ऊपर वाला नोट नहीं किया सर
okay, no, I will share this PDF file with you. Okay, so don't worry about okay. So then Einstein came and he suggested some radical changes. Yeah.
Sir, Fy equal to Fm, how you did this, sir?
So no, Fy means this is the force on the ball which is moving with velocity u. So u can be anything. Okay, it doesn't have to be constant. Okay, so the force on the ball is Fy. This is you are measuring. So that's why I put y subscript.
Yes,
M du by dt.
yes.
Fine. Now I want to measure. I want to measure the force on the same ball. Okay, but I am moving with velocity v with respect to u. So how would I measure it? So F me would be m. So this is u. This is me. So Fme is equal to m dum by dt, because the velocity of the ball with respect to me would be u minus v. Okay. So what is um? Um is u minus v. Now you take the derivative. Now since u can be anything, it can be accelerated. This is non-zero. But dv by dt is 0 because I'm moving with constant velocity with respect to u. Okay. So dv, so v is 0. Oh, sorry, v is constant. So that means dv by dt is 0. If dv by dt is 0, so that means Yeah, the force that you will calculate on the body, on that ball, and the force that I will calculate in my frames are equal. Okay. So yeah, I was saying, yeah, then there is something wrong and we have to figure it out. And then Einstein came and he suggested many radical changes. And one of the radical changes was loss of simultaneity. The loss of simultaneity. Okay, let me write simultaneity. Sorry, I'm getting a call. I'm sorry, simultaneity. Okay. And it says that the simultaneity means this thing. Suppose you are at here. Okay. Let's say you are at here, this position. So T and X. Okay. And suppose two lightning happen at equal distance from you. So one lightning happened here, one lightning happened here. Let's call this as event 1. Event 1. Let's call it event 2. Okay. This distance and this distance are same. Okay. This distance and this distance are same. Okay. It happened. Now let's analyze the same event with respect to an observer. Let's say me, which is moving with velocity v with respect to you. What will happen? So the observer you will say that event 1 and event 2, I'm sorry, event 2 are simultaneous. Why? Because the signal from event 1 and the signal from event 2 reached you at the same time. And you happens to know that they are at same distance. Okay, you position yourself such that these two events these two lightning happens at the same distance from you. And if the signal from these two events reach you at the same time, you will say, yes, the event 1 and event 2 are simultaneous. They happened at the same time. But now analyze the same event, same scenario with respect to an observer who is moving with velocity v. Well, with respect to velocity v, the observer will say, no, the signal from event 2 will reach first. Why? Because by the time light reach you, you have already traveled a distance vt in the direction of event 2. So the distance is less. And you will say the event 1 happened later. So you will say no. Event 2 happens first, then event 1. So according to you, according to a moving observer, according to the moving observer, the event 1 and event 2 are not simultaneous. Okay, the event 2 and event 1 are not simultaneous. And if that is the case, what do you mean by simultaneous? They happen at the same time. Okay, so for example, let's say this is you, t and x. So all point on this horizontal axis are simultaneous because they happen. So this point, all events that happen at this are simultaneous. Similarly, all events that happen on T2 are simultaneous. Okay. Similarly, all events that happen at T0 are simultaneous. So these two events are simultaneous. Okay. If these two events are simultaneous, then this approximation that t prime is equal to t may not be correct. May not be correct. May not be correct, or you have to be very careful while using t prime is equal to t approximation. Okay. Is this clear now? Is this clear? The concept of yeah.
No, sir.
Again,
Sir,
Last
sir,
one.
explain. Yes, sir.
Okay.
Last
So
one.
okay, good, good, good.
And the
Now, good. Just wait. Okay. Imagine that you are sitting at your home, and just 1 kilometer to your left and right, you just forget about all other directions. Two lightning strikes. Okay. Light moves with velocity c, so that two lightning will reach you, okay, at the same time. Yes or no?
Yes.
yes, sir.
Okay, good.
Yes.
If they
Yes, sir.
good. So if it reach at the same time, you will say this event 1 and event 2 are simultaneous because they are happening at the same time. Okay. Now you imagine you are moving with velocity v towards the second event. Okay, you now analyzing the same situation. Two lightning happens. Now you are analyzing the same situation, but now you are moving towards the positive x-axis. What will you observe? Will the event 1 and event 2, two lightning will appear simultaneous to you?
No.
No, sir.
No. No, sir.
Exactly.
No, sir.
So that's the second statement, that the two events which are simultaneous in your coordinate system, in the rest coordinate system, may not be simultaneous in the moving coordinate system. Okay.
Yes,
So
sir.
that's a okay.
Okay,
So
sir.
that leads
you-
to
Okay, sir.
yeah. So that leads to this
you have
assumption that the t prime may not be equal to t. If it is simultaneous, means two events are happening at t is equal to 0, that may not be happening at t prime is equal to 0. Okay, so this approximation or this transformation that t prime is equal to t, which Newton suggested, okay, may not, or Galilean, Newton, or others suggested, may not be correct. Okay, is this clear?
Yes, sir.
you
Yes, sir.
Sir,
have
above,
Yes, sir.
Yeah. So
excuse me, sir.
Yeah.
Sir, above you have written, so according to the moving observer, the event 1 and event 2 are simultaneous. So I was confused on
Not,
that.
not. Oh,
Not.
I'm sorry.
Okay.
Yes,
Okay,
are
sir.
not. I am sorry. Thank you for reminding. Yes, sir. Oh, yeah, I'll make many mistakes. So yeah, thank you. This is an important point. Are not simultaneous. Very good. Okay.
Sir,
Yeah.
sir, is the loss of simultaneously entirely based on imagination?
No, it is not. You'll see many applications of it. Okay. So it's not imagination. Well, you imagined it, and then you found it that with that imagination, the laws of physics, the way Newton described, are incorrect. Okay, so that means there is something wrong in it. Okay, so let me give you the how Einstein arrived this idea. Okay, so he actually imagined this two situation, that two lightning happens, so at rest they will be simultaneous, and with respect to some observer who is moving, they may not be simultaneous. Okay, so what he was trying to do is he was trying to understand how light behave. Okay, and he tried to understand that if I travel, suppose the light is moving, and I travel with the same velocity v, same velocity. So my velocity is also c. So for you, light is traveling with velocity c, and I'm also moving with velocity c, and I want to see how the light is traveling. Then he figure it out that that light will be something like static. The electromagnetic field of that light would be something static, and that are not solutions of Maxwell equations. Okay, so this was all his imagination. Okay, so he figured it out that there is something wrong with the, either we have to give up the electromagnetic equations, the Maxwell equation, or we have to give up the Newton laws of motion. Okay, so these two were not consistent, and then Einstein suggested that it is the Maxwell equations which are correct, okay, and it's the Newton equations which are not.
Okay, sir.
Okay, okay. Now, what is the relation between T prime and T? Or more importantly, in this, okay, just look at this figure. Please mute yourself.
Can you explain that graph? What?
Which graph? The square bracket?
Yes, sir. Yes.
Yeah. So if two events, let me explain it again. Suppose this is, so you see the vertical axis is T, the horizontal axis is X. Okay. So on this axis, let's say T0, T0. On this axis, all the events will happen at the same time because time is same, right? This is 1, this is 2, this is 3, this is 4. We'll see that 1, 2, 3 and 4 happens at the same time. So all these events are simultaneous. Okay. These two events are simultaneous. 1 is simultaneous to 2, 2 is simultaneous to 3 and so on 4. Okay. Now this is with respect to you. You are at rest. Okay. So we want to find the points or the clock or the time in the moving frame such that the events are simultaneous as well. Okay, so this is with respect to you. I want to find a similar coordinate system such that, okay, so let me repeat it again. So at t naught, at constant time t naught, 1, 2, 3, 4, 5 events happen. So these 1, 2, 3, 4, 5 events are simultaneous with respect to you, but they are not simultaneous with respect to me. Okay, now I want to find the equation such that the points are simultaneous with respect to me. Okay, so we want to find the relation for the simultaneity continuity for the simultaneity for the moving observer, moving observer. I don't know what that observer is. I don't know how we will find it, but I want to find it. How we will find it? We will find it using the two postulate that Einstein suggested. So
Sir,
postulates.
should we add that here C is constant?
Yes, C is constant. Okay, so let me. Yes, C is constant. C is always constant. Okay, so that's the postulate of relativity. Let me just mention the postulate of relativity. If it's not understand, then you can ask me again. Okay, so postulates of relativity. So there are two postulates of relativity. First postulate is the same which existed even before Newton, even before Einstein. So Newton suggested it and everyone agreed with it, that the laws of motion remain the same in all inertial frame. Okay, so this was there is nothing new about it, we all agreed with it. Okay, we just saw it, F is equal to ma. That what Einstein did, what additional Einstein did. Okay, the additional thing that Einstein did is he suggested another postulate, and he said that the velocity of light is constant or same in all inertial frame in free space. Okay, so this is the postulate which Einstein added in physics. This is the statement that Einstein added in physics. The velocity of light in all inertial frame is constant in all inertial frame. Okay, whether you measure the velocity or I measure the velocity or somebody else measure the velocity of light, that velocity of light will always be c. Okay, the velocity of light will always be c. So these were the two postulates that Einstein suggested. Okay, should I continue? I can go on. I would like to go on. So yeah, please let me know if you are if you want to proceed. If you
Yes,
want
sir.
me to
So we may
continue.
do
No,
it
sir.
tomorrow.
Yes, sir.
No, sir.
So
Sir,
we
we
can
will
now.
just
We
be
may do it tomorrow,
sitting
sir.
for three and a
Sir,
half hours.
Proceed,
tomorrow.
sir.
I see. Okay, okay, fine,
Sir,
fine, fine,
please,
fine.
sir.
Yeah. No, I
Sir,
don't. Yes, just okay, okay, fine. I got the idea. So yeah, I understand that it's a. So tomorrow we have a class at 8 o'clock. Okay.
Yes,
Yes,
So
sir.
sir.
yeah, we'll
Yeah.
start from this
Yes, sir.
point. Okay. So
Okay,
It's a
sir.
post.
what we good. So what we'll try to do is we'll try to find a relation such that events are synchronized, just like just like t is equal to constant line. T is equal to constant line. Uh, describe T is equal to constant line. Describe simultaneity in the rest frame. In the rest frame. Similarly, please mute yourself. Similarly, please mute yourself. T prime is equal to constant line will this come on, please mute yourself. Will describe simultaneity in the moving frame. In the moving
So will you
frame.
send it PDF in our group?
Sorry,
So
just a minute. Let me complete and then I'll say. There are I don't know what students are doing. I'm saying constantly saying please mute yourself, but they are not. Is it hard to understand or what? Who is this guy? Like, so we want to find the equation of t prime in terms of t. Okay, so that will be the task, and I will take you through the journey of Einstein, what Einstein did, how he come up with his famous formula for transformation between coordinates and all that we will see in the next class. Okay, so yeah, that we will do in the next class. We will try to find the simultaneous event in the moving frame. Okay, so yeah, so thank you for today. We'll meet tomorrow. If you have
So I
any
have a
question,
doubt.
you can ask.
Sir,
Yeah,
attendance.
So I have a doubt.
Thank you.
yeah.
The attendance.
Attendance is being
attendance.
recorded. Your attendance is being recorded.
So I have a doubt about the inertial frame.
Yeah.
It said that a frame in which laws of motion holds.
Yes.
But the thing is,
No.
like.
No. Inertial frame is not the one in which laws of motion hold. It's a frame which is either at rest or is moving with constant velocity. So yeah, it's a non-accelerating frame. So yeah.
But you can argue that everything in the universe is accelerating, so there will be no inertial frame.
Yes, yeah, that is correct.
So the laws of motions will not hold for anything.
No, then you have to. So so that's the another way. Another word of this subject is special relativity. What is special? Okay, so I explained to you the word special. I explained to you the word relativity, but I didn't explain to you the word special. It's a special in the sense that it applied to a restrictive system. What are those restrictive system? That restrictive system is that all the motion or the frames are moving with constant velocity. Okay, so if you have a non-inertial frame, accelerating frame, that accelerating frame corresponds to gravitational. Okay, so that is called, when you generalize our idea of constant velocity to acceleration, constant frame to accelerated frame, that gives you gravity. Okay, so we will not discuss anything about general relativity. We will only discuss about special relativity. Okay, the word is special for constant velocity.
Okay, sir.
So yes, just a minute.
One more
Let me
question.
complete. Just a minute. Let me complete. So you're right. There is very difficult to exactly associate a inertial frame. Okay, and because everything is moving with respect to everything. everything is feeling gravity of every other object. Okay, so in principle there are no inertial frame. Yes.
And so, and for the second that event you told one lightning, there are two lightning and one person is moving for a velocity v. That person for that the time will be slow down or something.
That we will see. That we will see. The answer is yes. So according to you, the person who is moving, its clock will slow down. Okay, so this is called time dilation. So we will see that in the next to next class or something. Okay.
And one more question.
Sir, please send this PDF, sir.
Yeah, I'll send it. Yeah.
Shall we leave?
Yeah. So those who wants to leave can leave, and those who wants to ask question, they can stay. But thank you. The class is over. Yes.
Thank you, sir.
And will light will be the only inertial frame?
No. That is also when you have a gravity. Okay, the light is moving in something. Okay, so the gravitational effect will also try to bend light. Okay, so in its own frame you can say you are inertial. In your own frame you can say you are in inertial frame. But in other frame you cannot say you are in inertial frame. The others will not say you are in inertial.
Sir, can I ask a question?
Okay, sir. Thank you.
Yeah, go ahead.
Sir, you told about the lightning problem in Rourkela, that event 1 and event 2, right? And when you were moving, you told that event 2 will happen before and event 1 will appear to happen later in your eyes. Right.
Yes.
But in the actual, if I am there, then I will see the two events simultaneously, but I will hear the sound late. Right. I will hear the frequency.
Yeah, so those are secondary effect. We are not discussing secondary effects. Okay, so that's a different thing, that sound moves with some velocity and light moves with some velocity. That's a
No,
secondary.
I am not telling that. I am telling that, sir. I am telling that event 2 sound will be greater than that of event 1, and you will think that event 2 has happened before and event 1 has happened later, but actually
There is no.
events
Okay,
that happen
let's say there
simultaneously.
is no sound. Let's say there is no sound. You are in vacuum.
Yeah.
There is no sound. Then
It will. I think it will appear simultaneously now, because
no, that's what
Yes,
I'm
sir.
saying. Na? You just forget everything. There is nothing existed.
Good, sir.
No sound, nothing, vacuum, nothing existed at all. Then you see two events, two lightning happen. Why it happened, how it happened, we don't care. This is a hypothetical situation. Okay, so you have a meter stick with you, some meter with which you can measure the length. You measure it. Okay, you position yourself such that the lightning happens such that it happened at equal distance with respect to you. One in the forward direction, one in the backward direction.
Yes, sir.
Now, those lightning will reach you at the same time. Because they have the same velocity, right? I'm not talking about sound and all.
Okay.
It happens. Light will reach you. It is a light. That means you can see it.
Yes, I now get it. I now get it. Yes. I now get it. Yeah.
Okay, good.
Thank you, sir. Thank you, sir.
Sir.
Okay, yeah.
Sir.
Yeah.
Sir, the second situation of that moving object seeing the two events. So that will be a hypothetical case, or we have to
No, it
accept
is not
that.
No, you just you can do this experiment if you want. Just close your eyes and try to think it. Okay, first put yourself at rest and then in motion. Then try to analyze it. You will come to the same conclusion. When you are at rest, two events are simultaneous. But when you are moving, the two lightning are not simultaneous. One lightning happens first with respect to the second lightning. Okay, you just close your eyes and visualize it.
Yes, sir.
Sir, I have another doubt. When you told that if I put a laser.
No, just a minute. I think somebody said it's difficult. Just at least to me, it's very clear. If it is not to you, then try to visualize it. Okay, it will be clear, because by the time. So where is this? Yeah, by the time you see, you are also moving, right? You are going towards the lightning.
So I got that problem. I understood. I am
Yeah.
asking another problem. I'm asking another problem.
What is?
When you told an example of about just lighting on a laser, right? When I am
Lightning on
lighting
a
on a laser,
laser?
yeah,
No, no,
laser
I'm not
lights.
lightning. No, 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 no. Laser light. Just to give you an example,
Yeah.
you flash a laser light from two different point. Okay, this is another example. Let's take another example that you are here. Okay, and you have a, this is you, this is your friend A, this is your friend B. Okay, you
Yes, sir.
ask your friend that exactly, so you synchronize your clock A, B, and C. Oh, sorry, you and A and B. You said at exactly 3 o'clock. At exactly 3 o'clock, you send me a light. So exactly 3 o'clock, he sends a light, and B sends you a light. Okay, this will
Yeah.
reach at the same
At the
time to
same
you.
time. Yes, sir.
Yeah.
Yes, sir.
Okay, so you have already measured the distance between you and A and B. So you'll
Yes, sir.
say, okay, A and B are synchronized. If you know that they are at equal distance from you, and you know that they send the sign at the same time, send the signal at the same time, then you know that both signal, and you know that the signals are reaching you at the same time. Then you can conclude that A and B are
At equal
simultaneous.
distance.
Not equal distance. Equal distance you already know.
Yeah, yeah. Okay.
Okay,
Yeah,
but
yes, sir.
okay. Now what you do is you analyze the same situation from a, now you are moving towards B. Okay, you again say
Yes, sir.
you you synchronize your clocks.
Yes, sir.
You synchronize. You say, okay, A and B, you synchronize your clock. But
Yeah.
I'm moving with this velocity. Okay.
Then B's light will come earlier.
Yes, because you have already moved a distance
Yes,
x
sir.
is equal to vt. So this B clock will appear. Will the signal from B will reach you first, then the signal
Yes.
from A. Am I
Yes, sir.
right?
Yes, sir. I completely understand it. I am not
Okay.
asking about this scenario. I am
Yeah.
completely asking about a different scenario.
Okay.
Please listen to me. Pardon me, sir. Actually, I am asking that if I am moving and lighting a flashlight, right? The flashlight from the earth, its speed will be c, the velocity of light. And if
Mm-hmm.
I am also moving with a
Uh-huh.
flashlight. My speed will be
Uh-huh.
v. Let's suppose my speed will be v, but
With
I'm
respect to
let's
whom?
yeah, with respect to the earth, my
Okay, so
I have a
okay,
constant
good,
velocity
good,
v.
good. Just a
Okay,
minute.
sir.
I'll
And
let me first understand it. Just calm down, calm down. So this is
okay, sir.
Earth.
Yes, sir.
Okay. So with respect to Earth, you are moving. You are is so this is you. You are
Yeah,
moving with velocity v. Okay,
v.
good, good.
And I have a flashlight in my hand.
Okay,
Yeah, and I am lighting on it.
okay,
And
okay.
with respect to Earth, it should
Yeah.
have a velocity of c. It should have a velocity c
Yes,
because Earth is
absolutely.
an inertial frame, and
Yes,
I am also moving in constant velocity. So I am also an
yes.
inertial frame. So with
Okay.
respect to my eyes, the speed
Hmm.
of light should be c, right?
Yes.
Then why this is contradictory? Then the from
No,
the
it is
Earth,
not.
it should be c plus v. Why
No,
it
it
is
is not.
contradictory?
No, no, it is not. So both respect to you and Earth, the velocity of light will be c. That you will see. That is the
Yeah.
whole idea of special relativity. That you will see in the next 3-4 classes. Okay. The point is this velocity addition law. Okay.
Yes, sir.
That where did we do it? We did it somewhere. Let me just see. Yeah, so this, you see, we say that the velocity of light can be c minus v and c plus v if we
Yes.
assume Galilean transformation, right? So the velocity of
Yes, sir.
light seems to be different, but that is not the case. Okay, so this velocity cannot be directly added. It's not like a plus b. When you move
Okay.
with high velocity comparable to the velocity of light. Okay, so the velocity addition law will be modified in special relativity. It is actually modified. Okay, it is so
Okay.
happens that in some limit that velocity addition law reduces to the Newton's velocity addition law. Okay, that happens in particular limit that we will see. Okay, that happens because the velocity of light is so huge.
Yes,
Okay,
sir.
it's so huge that the Newton approximation works. Okay, so that we
Okay.
will see. I understand your question, what you're asking.
Sir, I have a question.
Just a minute, just a minute.
Thank you, sir. Thank
But
you, sir.
yeah, the answer to your question is that if you have a flashlight
Yeah.
and you switch on it, so the velocity of light in your frame will be c, as well as the velocity of light in Earth's frame will be c.
Will be C.
Okay. Yeah.
Okay.
How it will happen, we'll see later on. Yes.
Okay.
There was another question from one girl.
Yes, sir.
Yeah.
Thank you, sir.
Yes, sir. This is Aishwarya. And
Yeah.
my question was regarding when Newton agreed with Galileo. So the question is, when Newton agreed with Galileo, what if you wouldn't consider v as a constant velocity?
With constant velocity, because
What if he wouldn't consider v as a constant velocity?
because that the frame velocity constant. Hello.
Yes, sir.
If
No, I
if
could
the
not
velocity would
understand the.
not be constant, it will be a non-inertial frame.
It's a
So we
non-inertial
can't,
frame. Yes.
so we can't apply any laws of motion there.
Yeah. Yes, correct. Is this clear to you?
No, sir.
No. What
I
is you?
asked what if the frame wouldn't move in the constant velocity?
Yeah. So the correct answer for this is that this non-inertial frame actually corresponds to gravity. Okay. Inertial frame means you cannot distinguish one frame to another frame. Okay. Imagine you are sitting, you are standing and a bus is passed by, then there is, or a rail is passed by. Just imagine there is nothing else. Nothing else. You cannot tell whether the train is moving or the bus is moving or you are that one is moving.
Or I am moving.
Yes. Okay. One statement would be, okay, I am at rest and the train is going in that direction, in the positive direction with velocity v, if v is constant. Another equally correct statement would be, no, the train is at rest but you are moving in negative x-axis with velocity v. Okay. So if there is a constant velocity, relative velocity is constant, you cannot distinguish one motion from another motion. But if that velocity is not constant, accelerating, then you can distinguish, okay, which one is actually moving. Okay. So if you are going in a bus, some jerk happen. From that jerk, you can see, oh, it is me who is moving, not the outside world who is moving. Okay.
Yeah.
But if there is no jerk, you cannot say you are moving. There is a way to say it. You might be moving, other one is at rest, or other one is at rest, or another one is moving, or you are at rest. Okay. So both description are possible. But when there is an acceleration,
if it wouldn't be constant, then we had to apply the general theory of relativity here.
Yes. So we will not go to general theory of relativity. It's too deep. It is reserved for advanced courses. Okay. So yeah. So we'll not discuss general relativity, but yeah, we'll discuss the idea of the consequences and the results of special relativity. You will see that many beautiful things. Okay. So you don't have to go to general relativity to learn something exciting. So just wait for 3-4. Yeah, few more classes, then you will see.
Sir, I have a doubt.
Yeah.
Sir, in the last case of A and B, if you are moving at speed v, sir, and the last case would be like to be a Doppler effect.
Yeah, it will be. So yeah, we will also study Doppler effect. If they send signal, how the signal will get modified and all. We'll see. Yes, you're right. There will be a Doppler effect. And we will discuss it. So you are going slightly ahead of me right now.
So this case is same as the lightning case.
Sorry, no. Lightning, I'm giving an example. The example is that to give you an idea about simultaneity. Okay, simultaneity. So yeah, to mention that, you should be very careful when you say that two events are simultaneous. Okay. For example, yeah, you have to be very careful to say that two events are simultaneous. So this is to give you an example. Yeah, there was another question. Okay. If not, then thank you. We'll meet tomorrow at 8 o'clock.
Thank you, sir. Bye.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.